Subject of today's webinar is functional safety, SIL assessment and verification. And specifically, what we are going to discuss today is question that do proof test practices affect P&IDs? And this is related to combination of process engineering and the maintenance practices. So if during the webinar you have any questions, just write down your questions, and if I'm able to answer all of those later at the end of this webinar, I will do so, or I'll answer your questions separately later on by email. So a brief introduction to myself. My name is Mohammed Saim. I'm a technical safety and loss prevention engineering consultant with more than 20 years experience in process industry. I'm working as a consultant since the year 2014. And before that, I've worked with BDO, BB, and Anglo Corporation. And my experience, core experience is in QRA, quantitative risk assessment, fire, explosion, and toxic hazard management studies, building risk assessments, hazard analysis and risk assessment studies, hazards, HAZOP, SIMOPs, SIL studies. I am running a consultancy services company by the name of Shepherd Risk, and I'm based in Karachi in Pakistan. And we provide process safety management services, implementation, audit of PSM, qualitative risk assessment workshop, quantitative risk assessment, fire, explosion, and toxic hazard management studies, and other process safety studies. We have provided services from Far East, Middle East, West Africa, Europe to UK. And there are various national and international clients we have served so far. Coming to the topic, so functional safety or SIL assessment. This subject is covered by international standards ISA and IEC. We are going to talk more about IEC, and IEC has two types of standards, one for the equipment manufacturer, IEC 61508, and the others are for the end users, for nuclear industry, for machinery, for process industry, and for road vehicles. So we are mostly related to the process industry. So we use IEC 61511 in combination with IEC 61508. Okay, so P&IDs. So when process engineers develop these P&IDs, they base their design based on their experience, RAGA gaps, industry practices, international practices, local regulations, and other considerations. And there are other considerations that may include the operational reasons or maintenance reasons. So when we do a process safety review, we ask certain questions. Is design safe enough? Do we have enough layers of protection? Will these layers of protection provide adequate risk reduction? Will these layers of protection function as desired when needed? So this is the process safety regime, and the answer to these questions is in design practices, engineering and installation practices, and operations and maintenance practices. And this overlapping regime is the process safety regime. So in order to find the answers to these process safety questions, we need to have a combination of application of design, engineering and installation, and maintenance and operation practices. So this is typical layer of protection hierarchy that we consider in our designs, starting from process design, process controls, alarm and operator interventions, and safety instrumented strips. And then there are mitigation layers such as active protection, passive protection, and ERPs. Our subject, SIL assessment and verification, is related to safety instrumented systems. So we are going to talk about only the safety instrumented systems in this webinar. So is an example case. We have a two-phase separator designed for 1250 psig at 220 degree F. The inlet stream is having a maximum force pressure of 2500 psig. There are two outlet streams, one liquid stream and one gas outlet stream, and there is a pressure controller at the gas outlet stream. We have a PSV on the pressure vessel set at the design pressure of 1250 psig. Our process hazard analysis highlighted a scenario that if there is a blocked outlet of the gas stream, the vessel will be subject to an overpressure of 2.5 times over its design pressure, which is good enough to rupture the vessel, and hence consequently leading to fires or toxic releases. To prevent that scenario, one safeguard is the conventional PSV, and then from our experience, we have provided a PSHH on the gas stream, which trips the inlet stream using an ESD or shutdown valve. When the pressure reaches the set pressure, this logic solver shuts down the inlet stream, so the vessel is not exposed to pressures beyond the design pressure. So we ask the question, is the residual risk low enough? And we need to find an answer to this question. So first thing is we need to understand the risk and what is a low enough risk. So risk is normally represented in two forms. Individual risk, which is the risk per year to an exposed person, could be an operator or maintenance personnel or any other personnel inside the working boundary. And the societal risk, which is cumulative risk per year of specified number of fatalities. Then we need to look at what is acceptable risk. So this is the company criteria, and in some countries this is the legal criteria. So we have to set and adopt whatever the criteria is there. If there's a legal requirement, we have to comply with that. If there's a company criteria, we have to adopt that. This is a typical or most widely used criteria based on UK HSC risk acceptance criteria, which is the upper limit of risk to a worker is 1 in 1,000 per year. Beyond this value, the risk is unacceptable. And the acceptable region is below 1 in 100,000 per year. So between the two, the minimum and the upper region is the allowed region. Our goal is to operate in acceptable region. However, this is not always possible due to various factors finances, economic, or other reason, as generally we operate somewhere here in the yellow region, which is the allowed region. So we target a risk which is as low as possible, below 1 in 1,000 per year. All right, so what we do in a risk analysis, we define our tolerable level of risk, and we analyze the inherent risk. That is the risk without taking credit of any safeguard. If the inherent risk is below the tolerable level of risk, then fine. We need not to have any further risk mitigations. So this is the line below which we need to operate. If the risk is above the inherent, the tolerable risk level, then we need to carry out a layer of protection analysis and bring the risk below the tolerable level by making design changes, such as increasing the design pressure of the pressure vessel itself, maybe. Other risk reduction measures, maybe reducing the manning level, reducing the exposure, and by providing safety instrumented functions. So all of these layers of protection reduce the risk to a certain level. And finally, we target to come below the tolerable risk level. The risk reduction associated with safety instrumented functions is measured in terms of SIL levels. And this is often represented as risk reduction factor, or conversely as probability of failure upon demand, 1 over PFD. So this is the IEC SIL levels table. SIL 4 being the highest safety level, SIL 1 is the lowest safety level. SIL 1 represents a risk reduction factor between 10 to 100, or conversely, a PFD between 0.1 to 0.01. Similarly, the SIL 2 is a risk reduction factor of 100 to 1,000 times. So we have a safety function in our design. We have a transmitter, pressure transmitter, a logic solver, and a final element, an ESD valve. The pressure transmitter detects the rise in pressure, and it gives an input to the logic solver, which gives an output to the ESD valve to shut down within certain period in our design. So this is the safety function we are talking about. Now assume that, and we make this assumption without making a detailed layer of protection analysis, assume that we associate a risk reduction factor of 400 to this PSHH. That is the SIL 2. So this function needs to be a SIL 2 with a risk reduction factor of 400. And we have to prove that throughout the life cycle of this facility, this risk reduction factor is maintained. That is, if the life of the facility is 20 years, throughout the 20 years, the PSHH will provide a risk reduction factor of 400. So how we demonstrate that this is going to be provided? Okay, so IEC 61511 and 61508 requires us to comply with 3 requirements. 1, the system is capable to meet the required SIL level, which means the components are designed to the desired SIL level, and that there are management systems in place to maintain the components in that SIL level condition throughout the life cycle. We are not going to talk about this in any detail and today. The second constraint is to meet the architectural constraints. That is the configuration of the safety function meets certain minimum architectural requirements. And number three is that by carrying out probability of failure upon demand calculations, which are based on the failure rate of the components, we prove that the PFD of the function is meeting the required PFD. And this tiny overlapping regime is the SIL compliance. If we are not meeting any of the three, but two, we cannot say that the function is in compliance with IEC requirement. So we need to meet all the three, but today we are going to talk about the PFD based on failure rate calculations. So any component, any hardware component can randomly fail in either safe way or in a dangerous way. So the safe failure is like it does not inhibit the safety function. It still functions, but maybe there are certain failures, or it brings the system to a safe state, also called a spurious trip. Dangerous failures are those failures which inhibit the safety function of the loop safety instrumented function. Now, there are diagnostics in some of the hardware, some smart transmitters or PLCs or other hardware which we use in our safety function. They have diagnosis, and some of the failures can be diagnosed or detected. Those are called the detected failures, and those which are not detected are the undetected failures, and they are the matter of concern. So if any failure is detected, be it a safe failure or a dangerous failure, by diagnostics of the component, it raises an alarm, and hence we dispatch a maintenance team out there in the field, and they rectify the issue by either replacing or doing maintenance or addressing the issue. So we restore the functionality within a specified period, which is maintenance time. Now we have to remember this safe failure fraction for use later at the end of this presentation. The safe failure fraction is the fraction of total failures that are detected, those are safe or those are dangerous. So all the dangerous failures that are detected are considered safe, because we can take action and restore the functionality within a certain period of time, and all the safe failures. So that's ratio of the detected plus the safe failure to the total failures is the safe failure fraction. We'll come back to this later at the end of the presentation. Now let's do the probability of failure calculation, and let's understand how it is done. Let's take an example scenario. We have a basket full of 100 balls, 99 of which are white and one is red, and this red ball is randomly distributed within the 99 other white balls. We are asked to pick one ball per hour randomly. So what is the probability that we pick the red ball in the first hour? 1 out of 100, because there are a total 100 balls. If we pick a white ball, you put it outside the basket. Now there are 99 balls, so in the next hour, the probability of picking randomly the red ball is 1 out of 99. If again we pick a white ball, we put it outside and we continue until the 100th hour, when there's only one red ball there, and hence the probability of picking the red ball is 1. And this red ball represents the dangerous failure or the incident itself. So the probability of failure increases with time, And the formula for the failure probability is 1 minus exponential times minus lambda, that is the failure rate, times the time span. Now, normally the lambda t is very, very small compared with 1. So this equation simplifies into failure probability equals to lambda times the time span, the time in hour, if the failure rate is in hours. So this gives us a straight line, diagonally straight line. We see that the failure probability increases with time as a product of the failure rate times the times lapse. Now, if at the 80th hour, we put all the white balls back in the basket, then at the 81st hour, at the 80th hour, the probability was 1 out of 20 because 80 balls have been removed. But at the 81st hour, it is restored back to 1 out of 100 because we have put all the white balls back in the basket. So again, the probability has been restored to 1 out of 100. And so this cycle continues. This restoration to its original position is called the proof test, and this time after which we restore the system to its original condition is termed proof test interval. And the average probability of failure upon demand during the proof test interval is simply by mathematics 0.5 times lambda d times test interval. So here on here, we operate until the PFD reaches the desired point. Then we do the proof test, restore the system to its origin, and then operate again. Then again, a proof test interval. And so we carry on with proof test and operation cycle. And the average PFD is maintained at a desired level. So we calculate the PFD for each of the components of the safety function, that is for the sensor, the logic solver, and the final element. And we sum that up to calculate the PFD of the safety function. And then we compare this with the target risk reduction factor. We set in the risk analysis or LOPA. And we compare if we are meeting the PFD for the function with the risk analysis requirement. If not, then what we do. So if the PFD for the function is not meeting the risk analysis criteria or the required risk reduction level, then we reduce the proof test interval and repeat the PFD calculations and come to a repetitive or iterative process until we meet the desired PFD for the function. So what is proof test for ESD valve? A proof test may comprise of different tests. For example, PT1 is a partial valve stroke test. PT2 is a full valve stroke test. PT3 full valve stroke test at operating conditions. PT4 full valve stroke test and leak test. And PT5 is full valve stroke test at operating conditions and leak test. So these are the five proof test requirements for ESD valve. There may be more requirements, but these are just some of the proof test requirements that are commonly required for a ESD valve. Now let's take an example of a ESD valve comprising of a solenoid, a poppet valve, actuator, valve body, assembly accessories, and each has a different dangerous failure rate. Each component is having a different dangerous failure rate. For example, solenoid is having a dangerous failure rate of 432 fits, and fits is failure in times measured in terms of one failure per 10 power minus 9 hours, 1 in a billion hours. So for each component of the ESD valve, we have certain dangerous failure rates. Total dangerous failure rate is 1,591 fits. Now, based on the proof tests, each of the 5 proof tests detects some of the dangerous failures. For example, PT1 detects 43 out of 432 failures of the solenoid, and 287 out of 500 of the actuator, and 315 out of 549 of the valve body. In total, the PT1 detects 679 out of 1591 fits. That is 57% of the failures. PT2 detects 400, and so combination of PT1 and PT2 detects 1079 out of 1591, which is 74% of total fits. So similarly, PT3, combination of PT1, 2, 3 detects 79%, combination of PT1, 2, 3, and 4 detects 94%. And all the 5 tests together detect total 99% of the dangerous failures. So this represents a perfect proof test where almost all the failures are detected. 100% detection, restoration to its 0 position. Now let's assume that instead of putting back all the 80 balls back in the basket at the 80th hour, we put 70 balls in the basket after every 80th hour. So in the 80th hour, the PFD, the probability of picking a red ball was 120. And this time, after putting 70 balls back, the probability of picking the red ball is not 1 out of 100, but it's 1 out of 90. And this continues. And so at the 161st hour, that is the 3rd cycle, when we put the 70 balls back again, the probability is down to 1 out of 80. So with time, the PFD keeps increasing because we are not putting all the white balls back. That is, we are not restoring the system to its origin or its 0 condition. Hence, the system is not restored to its original PFD. So at the end of the proof test interval, we perform a CPT, which is not 100% perfect. So some of the dangerous failures remain undetected, represented by 1 minus CPT, that is proof test effectiveness is not 100%. So with time, we have seen that in the ball pit example, with time, the PFD keeps increasing. And so is the average PFD, that is 0.5 lambda D into test interval, keeps increasing with time until the average PFD exceeds our target PFD. So at this point in time, we need to stop and we need to overhaul or replace the hardware. And this time interval is called the mission time. So by overhauling or by replacing the hardware, we restore the PFD to its 0 or its origin. And so we start again from 0 our PFD cycle. So to take care of the effect of non-perfect proof tests, we have to add a factor of proof test effectiveness in our average PFD formula, CPT. So CPT times lambda D times test interval plus all the undetected failures accumulated over the mission time. And this is represented by the factor 1 minus CPT times lambda D times mission time. Now let's take an example to understand the impact of the CPT on the PFD. So we have a final element with the dangerous failure rate of 500 fits. We have a CPT of 80%, that is proof test effectiveness of 80%, and 1 minus CPT of 20%, that is 20% of the dangerous failures are not detected in the proof test. We set a mission time of 200,000 hours, that is around 20 years. That means that after 20 years, we will replace the hardware or carry out a major overhaul. Our proof test interval is 10,000 hours, around 1 year. We apply the PFD average formula, taking account of CPT, that is proof test effectiveness, 0.8 times lambda D times test interval of 10,000 years, plus 1 minus CPT times lambda D times mission time of 200,000 hours. This gives us a PFD of 1.2 into 10 power minus 2, or a risk reduction factor of 83. Remember, RRF is inverse of PFD. So we get an RRF of 83, which is a SIL 1. Now, if we had a perfect proof test, that is 100% CPT, and every other parameter remains the same, then we could have obtained a risk reduction factor of 400, that is SIL 2, from the same hardware and same mission time, same proof test interval. So the difference between a proof test effectiveness of 80% versus 100% is around 5 times in terms of risk reduction. So RRF for 80% CPT is 83, RRF for 100% CPT is 400. So our target was 400, right? So we meet the target risk reduction by carrying out 100% proof test coverage every 1 year. But is it practicable? So now we ask our operations and maintenance teams, do they allow to carry out all the 5 proof tests on the ESD valve? So we know that in most of the continuous processes in industries which operate 24 hours, 365 days a year, we do not normally allow online full valve stroke tests. Hence, PT3 and PT5 are not carried out normally in process industry. In oil and gas, in fertilizer, in refinery, that's something not normal. So if we are not allowing to carry out PT3 and PT5, then the total proof test coverage is 1165 fits out of 1591, which is 73% of the total failures. So our CPT or proof test coverage in this case will be 73%. So let's go back and see we can achieve 400 if the CPT is 100%. So when we take CPT as 80% and we still want to achieve a risk reduction factor of 400, what do we do? Okay, let's try another number for mission time, and this time instead of 200,000 hours, we take a mission time of 50,000 hours, that is around 5 years. And with 50,000 hours of mission time, we get a risk reduction factor of 222. It is SIL 2, but still not 400. So we reduce the mission time to 25,000 hours, that is around 2.5 years, and still we do not get to 400. We still get to 308. And if we look at the mission time of and if we get the mission time, look at the mission time of 25,000 hours or 2.5 years or 50,000 or 5 years, this sounds quite ridiculous when we talk about very big ESD valves. Nobody will allow the process designer to think that they are going to replace, say, a 20-inch ESD valve every 5 years, or carry out a major overhaul of a 20-inch valve every 5 years. Nobody will allow you. That's not an industry practice. So 2.5 years is a ridiculously short mission time. Hence, what to do? We need to achieve SIL 4. How to achieve that? So we conclude that the target risk reduction factor of 400 is not practicable to achieve with 1 out of 1 ESD valve because operations and maintenance philosophy does not allow full valve stroke test at operating conditions. Hence, the recommendation is to modify the design. So we modify the design and we go back to P&ID and we modify the P&ID by adding a second ESD valve in series with the first one. And we arrange the 2 ESD valves in 1 out of 2 logic so that in case of high pressure is detected, the logic solver PSHH gives signal to both the ESD valves to shut down. And even if one of them has failed dangerously, is not shutting down, the other is available to shut down and isolate the vessel and cut off the source pressure. So we do the PFD calculation again with CPT of 80% with mission time of 200,000 hours for 1 out of 2 logic. And these 1 out of 2 formulas, PFD formulas, are a bit more complex than simple 1 out of 1. We are not going into those formulas at the moment, but I will show the result. So with 1 out of 2 configuration, we come to a PFD of 2.2 into 10 power minus 3 and an RRF of 436. Right, so we meet our targets RRF of 400 by adding 1 ESD valve in 1 out of 2 configuration. Now this is how we learned that, okay, our experience told us that 1 ESD valve is enough. This is what I have seen in many designs. This is what is my experience. Normally I have seen these P&IDs, okay, fine. But when we do the calculations taking into consideration the maintenance and operations philosophy on the ESD valves, we come to the conclusion that we do not get the target risk reduction with only 1 ESD valve. Okay, so that was the objective, to understand how maintenance and practices or proof test practices can affect our P&IDs. Moving ahead, we talked about in STAR that the SIL compliance is about system capability, architectural constraints, and the PFD, probability of failure. So I'll touch a little bit on architectural constraints to strengthen our point of view on 1 out of 2 ESD valves. So this is the IEC 61511 hardware fault tolerance table. Okay, so this table shows us safe failure fraction versus minimum hardware fault tolerance. And there are two tables actually. One is for type A and the other is for type B. So type A hardware are mechanical intensive hardware such as switches or valves, and type P hardware are typically the smart transmitters or PLCs. Now we've seen that the safe failure fraction is the ratio of the safe failures and the dangerous detected failure to the total failure. So we need to know the safe failure fraction of our hardware. This info is normally provided by the vendors, but we know that the smart transmitters and PLCs have a very high safe failure fraction that is above 90%. But the mechanical equipment such as the valve, ESD valves, have a very low safe failure fraction because they do not have automatic diagnostics. So the safe failure fraction of an ESD valve will be less than 60%, and the valve is a type A type hardware. So our target SIL level was SIL 2. So if we want to achieve SIL 2 with as hardware having a safe failure fraction less than 60%, that is for ESD valve, we need a hardware fault tolerance of 1. Got it? Which means a hardware fault tolerance of 1 means either 1 out of 2 or 2 out of 3. So bare minimum, we need a 1 redundant ESD valve. That's what we provided here, 1 out of 2 ESD valves, right? So there's one point here to remember. Okay, let's assume our PFD calculations. Our PFD calculations tell us that the one ESD configuration can give us the desired 400 risk reduction. Let's assume it. Okay, so we will say, okay, with the PFD calculations, we can get the PFD of 400 with 1 ESD valve. So we'll provide only 1. But here we have seen that the IEC 61511 architectural constraints require us to have a hardware fault tolerance of 1 if using a hardware with a safe failure fraction of less than 60%. So in any case, we will be providing a 1 out of 2 ESD design on our P&ID. So that's the conclusion, and I hope you now understand that the consideration of operations and maintenance philosophies on the safety instrumented functions is important to get the desired risk reduction throughout the mission time or throughout the facility design time. So with that, we come to the end of the presentation. We have a few questions. I would like to see the questions. Okay. So the question is how to set tolerable limits. Okay, we talked about the tolerable limits, and I'll just go back to the tolerable limit is defined either by the country regulation, the laws, or by the company. So, for example, in UK, we have a legal requirement of tolerable risk limit. That is 1 in 1,000 per year. And this tolerable limit is adopted by most companies around the world, but like in Netherlands, this is most stringent. In Singapore, Malaysia, Hong Kong, it's different. So that's on company to company that which risk criteria they adopt. And this is just one example, which is from UK HSC that I showed you. Okay, so another question is dangerous failure rates are defined on which basis? Okay, so we need to know the failure rates of any hardware component and how we get those failure rates. So either the equipment is certified and tested, and so through FMEDA, we get the various failure rates. Those are tested failure rates, or we get the failure rates from user feedback, that is from the industry feedback, and we have a good database in Syntef, Orida, or other databases, and we can use both. So there's always a debate that which data is more accurate, whether the industry feedback or whether the certification agency's failure FMED approach. So both are good. There's not a major difference in both the data. So both are almost in good range within each other. So it doesn't make much of a difference to use either of the failure rates. One of the question is, what is the minimum and max test interval period? Okay, so we set the test interval based on the PFD calculations. As long as we achieve the target PFD set by the risk analysis, we can even set up a test interval of 20 years. Sounds ridiculous, but if the calculation says so, okay, fine, well and good. But normally we come to test intervals of around 3 years. That is for normal PFD calculations in a refinery or in a fertilizer plant. So 1 to 3 years is normally what comes out in PFD calculations. But again, for each specific condition, each specific SIF, we have to do the PFD calculations to determine the test interval. Is SFF can be calculated after performing FMEA? Yes, we need to know various failure modes, and we need to know the diagnostic coverage, and we need to know which of the failures are detected, which will remain undetected. All right, so please recommend reading materials. Okay, so IEC 61511-61508 are the governing standards. So from the standards point of view, you have to go to those, and they are very detailed, very in-depth. But remember one thing: the IEC do not account the CPT, the discussion we had. The IEC formulas are simplified formulas. They assume 100% proof test effectiveness. The EXIDA is an agency that provides a good material on functional safety, and they have come up with this CPT methodology. They have proved it that not considering the CPT can mislead in terms of the functional safety and SIL verification. So you can have the EXIDA material available. They have a very good set of webinars on YouTube. You can just watch those webinars for your learning. They're very simple, very effective, and very good webinars. Mission time could be the time period between 2 consecutive turnaround overhaul. Well, if you can afford to overhaul your EST valves or your safe safety function every 2 consecutive turnarounds, well and good. But it's quite cost intensive if it involves big EST valves or it was a number of EST valves. So if there are hundreds of EST valves in a facility, you cannot overhaul all of them within 5 years or within 10 years. So you have to plan a longer mission time so that it is cost effective. All right, so we are coming to the end of the hour, and I believe there are a lot of questions still pending to be answered. So what I'll do that I will try to answer those questions individually to all of you. If any of you like to ask me directly, you have my email. Just drop an email to me, and I'll be happy to answer your question as much as I know. So this is an evolving knowledge base. Still, people are trying to learn and add more value to this safety function and knowledge base. So it's going to evolve more in coming years. So there's this one caution that, okay, if you are using ISA standard, then ISA further simplifies the IEC formula. So ISA gives a very, very conservative value. And ISA formulas can mislead to a very large degree. So, so I recommend you go for IEC formulas, and further you augment with the EXIDA add-ons on the IEC formula. So EXIDA add-ons are available through their publications, their books, and so you can have a combination of EXIDA and IEC. So with that, I conclude my webinar, and I hope you guys had a good time, good 1 hour. I'll try to answer your questions through email. Just if I miss answering your question through email, just give me a reminder, and I'll be happy to answer your question. So with this, I thank you all. Thank you for your time. I appreciate your time. There are a lot of questions coming up. So it's very difficult for me to hold on because not everybody has this spare time. So I conclude this webinar here, and we hope to meet some other time. I'll have another webinar in a while with you guys. Thank you so much. Thank you, everybody.